So, if we were at school, you would have just written a test on Unit 1, which was kinematics. We're moving into Unit 2 now, which is dynamics. So a little bit different. We're going to be talking about forces and how they are going to affect the motion of a lot of different objects. So today's lesson is on Intro to Forces. What's a force? How do we measure it? And what is it good for? So I already alluded to this fact. We just finished our kinematics unit. Our kinematics unit, hopefully you remember, is concerned with motion of objects. So we were looking at objects speeding up, slowing down, moving at a constant speed, moving at a constant velocity, all that sort of stuff. Dynamics is taking that essentially one step further. Dynamics is concerned with the motion of objects, same as kinematics, but we also are concerned, and the reason they're moving. The reason they are moving. So instead of just saying they are moving now and doing calculations, we're going to look at saying they are moving and why are they moving. Together, if we put those kinematics and dynamics, we get something referred to as mechanics. So when we talk about mechanics, we're talking about kinematics and dynamics together. So if dynamics is concerned with the reason objects are moving, not just the fact that they're moving, but also the reason why objects are moving is because of forces. So let's give a definition of a force. Force is just an interaction between two objects. And usually we just think of these, so we think of forces as pushes or pulls. So one object is pushing or pulling on another object. When we talk about forces, the unit of force in SI, so our system international, or our metric system, is the Newton. And this unit, when we measure it using the symbol N. That's a big N. Now, one thing that we need to carry over from before when we were talking about vectors, force is a new vector. So force is not only going to have a value, it's also going to have a direction. So that's really important that we keep that in mind. All right, so we're going to look at a bunch of different forces in this class, but the first one, and the one that we're going to encounter the most frequently, is the normal force. So what is the normal force? So let's write a definition here. The normal force, and when we write it, we're going to confusingly use the letter N to mean the normal force, which is also the unit of a force, or sometimes we call it F with a subscript of N. So F for force, N to talk about the normal force. So the normal force is the force a surface applies to an object acting, I should have a comma there, acting perpendicular to the surface. All right, what does that mean? That means if something is on a surface, then the normal force is pointed the perpendicular to the surface. So let's just talk about this for a second. Let's look at an example. So let's say I've got a book. Let's try to draw my book here. Hey, that's not terrible, is it? So here's my book. If I'm just holding it up in the air and I drop it, what forces do we have on it? We just have gravity working on it. And so we would draw it as an arrow like this. Remember, a force is a vector, so we're given it direction, and we'd call this Fg, which is just the force of gravity. So if I'm just holding it and I let it go, that's the only force that's acting on it. Well, what about if we put it on a table instead? So now we have our book. You're all holding your breath, seeing how well I'm doing with drawing. We have our book, and it's sitting on a table right here. It looks like it's kind of hanging off the edge, but that's okay. So it's sitting on the table. So we still have, let's use a different color here. We still have gravity trying to pull it down, but what happens? That table holds it up. And that means there's a force actually going in the opposite direction. And it's perpendicular to this surface, and it's this one. And this is N, or the normal force. So this is perpendicular to the surface that it's on. What if I hold a book against a wall? So basically, we're going to have, let's see, a wall here. We're going to have my book. Ooh, this is going to be tricky to draw. I don't know if I can do this, guys. Ooh, 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 ooh. Okay, let's pretend that that's a book. I don't even know where the pages are supposed to be. Here we go. Here's the wall. Well, if I'm pushing it, well, let's look at all the forces that we've got here. What have we got? Gravity's still trying to pull that down, so we've got the force of gravity. What else is going on? I'm pushing it against the wall, so guess what? I'm pushing into it, so there's a force here. We'll just call it F for force. And guess what? The wall's pushing back at me. That seems strange, but think about it. I'm not pushing it through the wall. I'm pushing really hard. And it's not being pushed towards me, so the wall's actually pushing back, and that is what's called the normal force. It's perpendicular to the wall. It's pushing back out. So long as I'm pushing it there and it's not moving, it's not going in, it's not coming out. So the normal force is just a force that is perpendicular to the surface. That's going to be important as we move along here. So let's talk about something that goes along with this intro to forces, is this concept of weight versus mass. So I know you've talked about this in your other classes before, so this should be pretty quick to go through. When we talk about in physics, it's really important that we differentiate between weight and mass, that we don't get those two confused. They're measured with different units and they mean different things. So mass is just a measure of mass is a measure of, there we go, the amount of matter in an object. So that's not going to change no matter where you are. So long as you are at home, you're at the top of the Empire State Building, you're at the top of Mount Everest, you are under the ocean, you're way out in space, your mass, if I could just snap and transport you to one other place, your mass would stay the same. You can't transport anywhere right now. You're stuck at home. Let's be clear on that. Stay home. But your mass stays the same. So when we measure mass, we measure it in the kilogram. And our units are kg. All right, that's pretty easy. What's the difference between mass and weight? Well, weight is the force of gravity acting on an object. So it's actually gravity acting on the mass. So that's important, that weight is the force of gravity acting on the mass. So what does that tell us? Well, if gravity changes, the weight's going to change, right? So when we're out in space, gravity is different than when we're here at home. So the weight is going to change. That's why we say you're weightless when you're in space. However, the mass is still going to be the same. So when we talk about weight, what unit do we use here? Well, it's a unit of force, and you guessed it, it's the Newton. And we use N as our unit. So on Earth, when we talk about Fg, and I should have mentioned that here, that's the force of gravity. I think we had that on the last slide. How do we actually calculate it? So here is a formula for you. So Fg equals, and it's a nice easy formula, m times g. So what do these three things mean here? Well, we've already said Fg is the force of gravity. M, hopefully you've guessed it, is mass, and that's going to be measured in kilograms. And g is acceleration due to gravity. And you guys were doing some questions with that, so we should remember that that is going to be in meters per second squared. And here on Earth, our accepted value is 9.81 meters per second squared is our accepted value on Earth. And that's actually going to change if you are under the water, if you're at sea level, or if you're way up at the top of Mount Everest. That's going to change ever so slightly, but this is the value we're going to use. So let's go ahead and do a question based on this formula. Pretty easy formula, only 3 variables to deal with. So your example is, what is the weight of your 73 kilogram teacher here on Earth? So later on we'll put me out in space and all that sort of fun stuff. But for now, let's say I'm here on Earth. Doesn't always feel that way, but let's say I am. So I'm asking you, what is the weight of me? So let's identify things. So F, G, M, and G. So let's fill some stuff in. We know we're here on Earth, so G is 9.81 meters per second squared. And really we should be putting in units, so this is down. We should be putting in direction, so that's down. My mass is 73 kilograms, and we're asking what is the weight? That is Fg. What is Fg? So we just write down our formula. Fg equals m times g. Pretty easy calculation here. Mass is 73 kilograms. Gravity is 9.81 meters per second squared. Down. And we just multiply those. So 73 times 9.81 gives me, when I round to 2 significant digits, gives me 720. Now, we didn't talk about what our units here are, so we can't cancel anything. So this unit is actually kilograms times meters per second squared. And let's give a direction of down. Now, kilogram meters per second squared is not a very kind looking unit, but in fact, that is actually a Newton. So this is equal to 720 newtons down. So maybe you want to write that in your notes here, that 1 Newton is defined as 1 kilogram meter per second squared. That's actually the definition of the unit Newton. So 1 Newton is equal to 1 kilogram times meters per second squared. So you can feel free to leave your answer either this way or this way. Personally, I like writing it with newtons, especially when we start rearranging this formula and we're given values for the weight in newtons to begin with. So what I'd like for you to do now is try these 3 questions on the last slide of your notes, and best of luck.